So in this video, I want to talk about thermodynamics and just a little bit of review. How would we, just label a graph and relating Gibbs free energy to entropy and enthalpy, right? So remember we said that KEQ, which is the equilibrium constant, and that's just the products over the reactants, right? Now remember we said reactants, right? Now remember we said, right? So as KEQ gets larger, right? Gets really large, products are favored, right? Products are favored, right? Can't spell right now, but that's okay, right? So the products are favored, right? Now, the one thing I want you to take away from this, kind of lesson is this equation, Gibbs free energy, right? When we relate delta G, it would say delta G is equal to delta H minus T delta S, right? Remember we said that S, right, is delta S, we kind of relate that to some sort of entropy, right? And remember we said that, okay, well, in order for the reaction to be non-spontaneous, right, in order for the reaction to be non-spontaneous, right, delta S has to be negative, right? So this is non-spontaneous, right? And in order for the reaction to be, in terms of entropy, positive will make it spontaneous, all right? And we said that spontaneity, right? When it's positive, delta S is positive, we're increasing disorder in the system. So that will lead to a spontaneous reaction, right? So taking a good look at this equation again, right? Think about it, right? We said that if delta G is negative, then we have a spontaneous reaction, right? So think about it. If we want delta G to be negative, right, then therefore delta H has to be negative with delta S has to be positive, right? Because you could think of it in negative minus a negative, and no matter how big delta S is in terms of how positive it is, a negative minus a negative times a positive will always give you a negative answer. So therefore, if we want the system to be spontaneous at any given time, then delta H has to be negative. Well, I've just put -1, but that's okay. Delta H has to be negative, and or delta S has to be positive. And this corresponds to spontaneity, spontaneous reactions, right? And then the opposite is true. If you want this to be a non-spontaneous process system, then delta H has to be positive, and then delta S has to be negative, right? And you could think of delta S as we're decreasing disorder in the system, right? So that's just a quick review. So let's go through a couple examples to kind of nail this concept down, and let's look at a few diagrams. So taking a look at this energy diagram, right? This is a reaction from A to B, right? And so this one says put an X in the correct boxes in the following, right? If the free energy of the product B was lowered, keeping all other energies of the starting materials and the transition state unchanged, which of the following would happen, right? So would the final equilibrium constant increase? Would the final equilibrium constant decrease? Would the overall rate of reactants going to products increase? And would the overall rate of the reactants going to products decrease? Well, remember we said that, okay, well, if we're going to lower the energy of the product, right? So if we're going to lower the energy of B, right? If we're going to lower the energy of B, think about it. If we lower the transition state has everything in the world to do with the rate of the reaction, right? Because remember, that's your energy barrier that the system has to cross in order for that reaction to go faster, right? And so that's why we add catalysts. So therefore, I could eliminate these two because the rate of the reaction would not be dependent upon the lowering the energy of the products of the reactant. The rate of the reaction doesn't depend on that at all. That's actually the transition state. So therefore, I'm looking at this and I'm saying, okay, well, the equilibrium constant, yes, that's viable, right? Because you could think of it. If you lower the energy of the products, right? If you lower the energy of the products, then again, what you're doing, right? What you're doing is increasing the reaction, right? That would increase the reaction, right? Because remember, it's B divided by A, right? It's B divided by A. So this would increase the overall equilibrium constant would increase because you could imagine lowering the energy, right? So you're lowering the energy barrier products. Right? So this is going down, which means that you're getting more of your product, which means that your equilibrium constant will increase. And that will be the only answer for this. So let's take a look at the other one. So this one says if the transition state was lowered, keeping all, lowered, keeping the energies of A and B unchanged, which of the following would happen? Well, think about it. If you lower the transition state, this is just a one-step reaction. So this is from A to B. So therefore, here's our rate limiting step, right? Here's our rate limiting step, right? So you could think of it. If we lower this, right? You could think of it. If we lower this, then therefore the overall rate of reactants going to products will increase because you're making the energy barrier smaller, right? So taking a look at this versus this now, if you lower this to this, look at that. That's just a quick, fast reaction. The rate, boom, 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 super fast, right? So that's the difference between lowering the transition state and kind of messing around with your products and reactants. Now let's take a look at the, just a standard energy diagram, and we're gonna do some labeling here, right? Now, is this an endothermic reaction or exothermic reaction? Now remember, exothermic reactions, your reactants are always higher in products than higher in energy than your products, right? Your reactions are always higher in energy than your products, right? So this will represent an exothermic reaction, right? Now, if the roles were switched where your products were higher in energy than your reactant, then that would be endothermic. But this is an exothermic diagram, right? So the first part says to label the energy and reaction progress axis on the diagram. Well, remember, reaction progress is usually on the x-axis, right? Going that way, right? And then this is our energy, delta G, right? The y-axis is delta G, right? Now B says label the reactants in the product, right? So again, these are my starting materials on an energy diagram. So you have the reactants, right? And then the products will be here. Right? And these could be whatever. This is just a illustration purpose for illustration purposes, right? So here's our reactants, here's our products, right? Now label the activation energy for the first and the second step. Now remember, for the first graph we saw that's just a one-step process, right? And furthermore, in organic chemistry, when we start talking about SN2 reactions and SN1 reactions, we will see that a two-step process very favors an SN1 reaction, where there's a fast step and a slow step, right? So therefore, if we were about to label this, right, then the first transition state is here, right? The first transition state is here, and usually it's denoted by this line and two lines through it, whatever. Right, so the first transition state is there. My second one is here at the top of the curve, right? So that's my first and second transition state. Right, now the activation energy, right? The activation energy barrier is just from this line here, your reactive intermediate, and this will be your activation energy barrier. All right, this is the activation energy barrier. All right, now these are intermediates. Anytime you see a line here, these are intermediates. All right, now is the overall reaction endothermic or exothermic? Well, remember, it's going to be exothermic, right? Because our products are higher in energy than our reactions are higher in energy than our products, right? So therefore, delta H has to be negative, right? Has to be negative. Now, which points on the curve corresponds to the intermediate? Oh, we already labeled that. Transition state, we already labeled that, right? So maybe we could call this, EA2 and then EA1, right? For activation energy, right? All right, so that will be activation energy. Here's our transition state. All right, so here's our transition states, kind of here and here on the top of that curve here. All right, now label the transition state and the rate limiting step. Now, which one's the rate limiting step? This is an interesting one. And the rate limiting step is going to be the one that has a higher activation energy or the higher energy barrier, right? So this one will be a rate limiting step. All right, this will be a rate limiting step. Now, what if on an exam they asked you, okay, well, what if you lower the, what if you lower the transition state of the second activation energy barrier? What would happen? And the answer would be nothing. Nothing would happen. You could lower it all you want, nothing would happen. Because the reaction is not dependent upon that step. The rate limiting step, right? The rate limiting step is what the reaction is dependent upon, right? So no matter what else you do here, this will not affect the overall rate of the reaction, whether it's going faster or higher. No matter what you do, if you higher this activation energy on EA2, it won't matter because this is not the rate limiting step. Right, the rate limiting step is all that is dependent upon how fast a reaction goes. So if you lower the rate limiting step, now your overall rates going to products would increase. All right, and the last one says draw a endothermic reaction and label with a rate limiting step. And endothermic reaction is just simple the opposite. Right? So you may have this is kind of not good. It's kind of not good, but for simplistic reasons, right? An endothermic reaction is just simply the opposite, right? So now your products are going to be, your reaction is going to be lower in energy than your products, right? And maybe we should draw one step, kind of bell curve looking thing like that, where this is our reaction progress and this is our energy. All right, as it goes up. All right, these will be our products, and these will be our reactants. All right, we have our transition state up here, right? And then again, this is a one-step process, so this will also be a rate limiting step. Right, that will be a rate limiting step. There's our activation energy. All right, we have our products, and that's about it. So this is just a kind of review, if you will, but it's just getting comfortable with these types of graphs and being able to read a energy diagram.